Hello there, Mr. Sutton bringing you this lesson on differential equations in one variable. As the title suggests, we're going to be solving equations of that type. Let's begin with a few definitions. What is a differential equation? Well, as the name suggests, it's an equation with a derivative in it. For example, dy over dx equals 4x minus 2. So what's the big deal here? We have seen derivatives before, but this is a slightly different take on them. We can talk about different solutions to a differential equation. For example, the general solution is just the general antiderivative equation for this thing with the plus c. And there's also a particular solution. This is a specific antiderivative where your c actually has a value. How do we pick that value? Well, this solution has to fit an initial condition. Now, what in the world does that mean? An initial condition is just a point that your solution passes through on a graph. For example, if I had written up here this differential equation and then y of 3 equals negative 6, I am giving you a point here that the solution to this thing has to go through, the point 3 comma negative 6. So to see what this actually looks like and means, I'm going to go to a Desmos here that I created. Bear with me. So here's a Desmos to kind of re-explain all of that stuff visually. This is kind of crazy looking if you've never seen one of these. This is a slope field. This takes a differential equation here, which you'll notice is basically our 4x minus 2 that we saw on that PowerPoint slide, and it takes every single x and y value that you could possibly want, plugs it in here, and gets a slope in return. All of those slopes are being graphed here at every x and y value point. For example, at 0, 0, if you plug 0 in here, you're graphing the slope negative 2. And we've just done that everywhere. So you could kind of think of the general solution to this differential equation as all of these different possibilities. But now, if we have a specific point that we need to go through, for example, 3 comma negative 6, then we can start to draw a curve that goes through this point and follows these slope lines. So here is a solution, a particular solution, but the c value on this one isn't quite correct. It doesn't allow us to go through this point. So if we start playing with that c value and adjusting it, we can eventually get a curve that follows the slope lines and goes through that specific point. And it happens to be the c value negative 18. So this is pretty much what we're going to be doing, is finding c values and writing antiderivatives, except we're going to have to do it without using Desmos. So at this point, we're actually going to solve this differential equation with this initial condition. First step, we just have to take the antiderivative. That'll give us the general solution. So that'll give us y equals, because that's the antiderivative of dy dx, so y equals, bump up the exponent to a 2, that'll be 2x squared minus 2x plus c. Now to get the particular solution with this initial condition, we just have to plug the initial condition in, solve for c, and then rewrite it with c actually filled in. So we know when x is 3, y is negative 6. So we can say negative 6 equals 2 times 3 squared minus 2 times 3 plus c. This is going to be 18 minus 6, so 12 over here. Subtracting that from both sides, we get a c value of negative 18. And don't forget to actually plug it back in. So our particular solution will be y equals 2x squared minus 2x minus 18. Here's another differential equation for you to solve. Pause the video and find the general and particular for this one. All right, so let's start by taking our antiderivative. So we're going to have y equals, and this is going to be negative 7 cosine of x plus c. But now we need to find the particular solution. So we're going to plug in, it looks like pi over 2 for x and negative 3 for y. So we have negative 3 equals negative 7 cosine of pi over 2 plus c. Cosine of pi over 2, well, that's actually just 0. So this is essentially negative 3 equals c. And then we can plug that back in to rewrite negative 7 cosine of x minus 3 equals y. Here's another example that you're absolutely going to love. Pause the video and give this one a whirl. All right, so for our antiderivative, we've got y equals negative 4 ln absolute value of x plus 6 plus c. Plugging in the initial condition, we've got y is all of this stuff over here, which is kind of crazy. And then over on the right side, negative 4 ln of absolute value of 2 plus 6 plus c. But this is really just ln of 8. So if we add this 4 ln of 8 over to the left side, those are going to cancel, leaving us with just c equals 5. And you probably went ahead and plugged this in up here and called it a day. Unfortunately, we can't do that. We have to drop the absolute value one way or another for that final solution. And to see why this is the case, I'm going to go back to Desmos. So here is what your particular solution would look like for that one if we left the absolute value in. And I've also put the particular solutions on here, or the initial conditions for examples 3 and also 4. Don't say I didn't give you anything. Now, why is this not okay? Well, a bunch of mathematicians essentially got together and agreed that they don't want any discontinuities in their particular solution. It's just going to be the biggest continuous piece of whatever you would have gotten. So because of this, we can't have this asymptote here at x equals negative 6. We have to find a way around that. So their solution is to get rid of this absolute value and just take the branch that goes through the particular initial condition that you're trying to go through. So for example 3, we want this branch. For example 4, when we have a different initial condition, we're going to see that we want this other branch instead. The key is we don't want both branches. We need to get rid of the absolute value one way or another. So how do we actually do that algebraically? Well, algebraically, we take a look at the initial condition and see what it's doing to the stuff inside the absolute value. If the initial condition makes the expression inside absolute value negative, we're going to negate the whole inside to force it to be positive. If, on the other hand, the stuff inside was already going to be positive with the initial condition, then we can just drop the absolute value and replace it with a simple parentheses. In this case, we have an initial condition with an x value of 2. If x equals 2, then the stuff inside here, x plus 6, is going to end up being positive. So for that reason, when we get rid of this absolute value, all we actually have to do is replace it with a simple parentheses. So we're going to have y equals negative 4 ln parentheses of x plus 6, and then don't forget to actually put your plus 5 in there. We're going to tie up one more loose end by taking a look at the differential equation that you just did for example 3, but with a different initial condition. Pause the video and see where you can go with this one. All right. So the antiderivative is still going to be y equals negative 4 ln absolute value of x plus 6. And plugging in the initial condition now, you still have this craziness for y over here. And now we've got negative 4 ln of negative 14 plus 6 absolute value plus c. The stuff inside here is now going to come out to negative 8. When you take the absolute value, though, you still have negative 4 ln of 8, which when you add it over here, basically cancels this and leaves you with c equals 5. This time around, though, if x equals negative 14, then this expression inside x plus 6 is negative. So we're actually going to have to negate this whole inner expression to make this work. So for my particular solution, I have to write now y equals negative 4 ln, and I'm going to use a parentheses, but now I'm going to write negative x minus 6. And then I'll still have that plus 5 over there. So that's it for our first round of differential equations. Till next time, Mr. Sutton signing off.